Hello, welcome to the Trenches of Cosmology. I'm Sean Hotchkiss, a part-time research fellow in Auckland University and part-time doer of things like this. Today, we'll be talking eventually about a particular paper that is using artificial intelligence. Hello, David, to look at cosmological simulations and predict stuff in the simulations better than previous algorithms have. And we are quite lucky to be joined at the moment just by one, but eventually by two of that actual paper's co-authors. So Helen will be joining us at about 45 minutes, but Francisco Villasqueza or Paco is already here. So let me just get him on screen and then he can introduce himself and say hi. I'll just unmute you. There we go.
Hi guys, so I'm Paco. Yeah, thank you, Sean, for the opportunity.
So we'll do a more thorough intro in a bit once maybe more people have joined, but we'll do the usual while we're waiting of just going through some of the most popular cosmology papers of the last month. So I was having some difficulty sharing my screen last stream, but we'll see whether that difficulty is happening again now, and I'll just have a go at doing that. If it starts being blurry, we'll have to improvise, but hopefully it won't be. All right, share this, I believe, should be the right thing. And then put the primary spot. Awesome. Awesome. So for those who haven't been in a stream before, this is a website where cosmologists can run their journal clubs, which is where they kind of get together to discuss recent papers. And on the journal clubs, they can vote if they want to discuss a certain paper. So you see here that in the last month, this particular paper had 47 votes, this one had 44, this one had 40. And I just want to use this for the first sort of 10 minutes or 15 minutes of each stream, just while people drift in so that they don't miss the main content. And also to give people watching the stream a kind of vision of what it is that cosmologists themselves are finding interesting. Sometimes these papers are upvoted not just because people find them worthwhile and interesting, but also because they might be a bit controversial. For example, number 3 is not actually about cosmology, but more about how to do cosmology. But it still gives an interesting idea of what people find interesting. Paper number 4 here actually has Francisco as a co-author, so I'm sure he'll be able to say a little bit about that. So yeah, this one at the top, the Atacama Cosmology Telescope Constraints on Pre-Recombination Early Dark Energy. So if we want to unpack that a little bit, this Atacama Cosmology Telescope is a telescope in Atacama, which is in the mountains in Chile, and it is measuring this cosmic microwave background, which is a relic from the early universe. And it is this recombination word is the concept. It's a really poorly termed concept for like the word is a bad use of language for cosmology. Hello, David. Two Davids. Hello, other David. And so what it is, it's the word recombine is meaning when the electrons and protons recombine in the early universe to form neutral hydrogen. It's a poor choice of word. Hello, Jerry. It's a poor choice of word because in the history of the universe, they've never been combined before. I think it comes from like atomic chemistry, where if you heat something up and then cool it down, the atoms recombine, and then they just use the same word for cosmology. But yeah, it's when the protons and electrons combined to form neutral hydrogen. And early dark energy would mean that there was some phase of accelerated expansion, or not accelerated expansion, but dark energy, like the dark energy we have now, but in this early epoch. Do you have anything you want to say about this, Paco? Paco being Francisco's name that he goes by more often than not.
Not Sean. Yeah, not much. Yeah.
Not much. Okay, so I'll just say a few things. So the reason why the CMB, the Atacama Cosmology Telescope, and therefore the CMB is sensitive to this kind of early dark energy effect is that the whole point is the early dark energy will be relevant just when the CMB is about to form. And if you're sitting there thinking that sounds a little bit fine tuned, then you're 100% right. There's no a priori physical reason why you would think that if there was some early dark energy, it should be relevant just when the CMB is forming. Hello, Deanna. Welcome from Helsinki. It's even later in Helsinki, I guess, now than it was when you were in Amsterdam. Well, where was it? Early dark energy. Yeah. So it has been suggested by some as a possible solution to this Hubble tension, although it's not very complete as a solution. to the Hubble tension. Wow, 11 p.m. But yeah, it might happen. And so then yeah, we mentioned the CMB and Deanna appeared. It's the consequences of this paper, and I think this is why this has been upvoted so much, is that it is very confusing what they're finding. I mean, if I open the abstract for you, you'll see certain certain things. So it sort of jumps all over the place. I'm not sure if this is big enough on your screen that you can see it, but using a combination of ACT, large scale Planck. So Planck's another telescope that's measuring the CMB, one that they put in space. Planck lensing in CMB says that it prefers early dark energy at 99.7 confidence limit. So in principle, this is saying that this data should only have occurred in 3 out of 1,000 realizations of the fundamental model, which would be obviously very, very unlikely. But then later on, they say that the preference for where was it? In contrast, a joint analysis of the full Planck and ACT data yields no evidence for early dark energy. So when they remove the polarization from Planck and don't consider the polarization, they get this very strong evidence for early dark energy. But then when they add polarization in, it goes away. So there's some mystery going on there. It could just be a random statistical fluctuation. If you look at 1,000 data sets, you do actually expect 1 in 1,000 to be so rare that they could only happen 1 in 1,000 times. It could be that there's some minor processing error going on in analyzing either the Planck or the Atacama Cosmology telescope data. Or it could be that, yeah, some fundamental new physics is going on that somehow the polarization is not affected by and the temperature is. So that was that paper. Then this one here, as I've told the regulars, thank you, Jerry. As I've told the regulars, this filtering that I do to get these most popular cosmology papers includes extragalactic astrophysics, and I'm not an expert on that. And so I don't actually know what a cooling and heating function are, so I can't tell you whether they actually exist. This paper here, Knowing When to Stop, was a kind of meta paper about the process of doing research and knowing when to give up on a model or when to give up on a paper and things like that. I haven't actually read it beyond the abstract, so I don't have a lot to say. I don't know whether, Paco, you have any thoughts on this particular meta paper either, or maybe Deanna, maybe you have some thoughts in the comments you want to add. Was that a no, Paco?
I didn't have time to read it, so unfortunately.
Yeah, I guess I can just talk on a kind of meta level. The reason why people sometimes worry about this and write papers about this is that observationally cosmology is kind of difficult because you only get the one universe to look at, and you can't design an experiment to rule in or out models. So we do have to be a little bit more thoughtful about when to give up on a model. You can't just design an experiment. You only have what the universe shows you. And even in the sort of kind of other fundamental physics, particle physics, even though they can design experiments, a lot of the time the experiment costs $5 billion and takes 20 years to build. So they're only in a marginally better situation than us. And so you really do need to know which theories you should be pursuing. I mean, in particle physics now, some of the theories are sort of 30, 40 years old, and we're still waiting to have funded final confirmation about whether they're correct or incorrect. Meanwhile, theoretical physicists are still building on them. And so, yeah, it is a kind of very tricky question to know what, as a researcher, one should commit themselves to. Yeah, Deanna. Sunday was actually my original idea, but then I thought that Monday morning for me would be too disruptive. But it turned out that Saturday morning was even more disruptive. That after a long week of work, I just didn't want to get up early and do a stream. But after a nice weekend, it seems more doable. Okay, Paco, you can't not have an opinion on paper 4 because you are the lead author. So, multi-field cosmology with artificial intelligence. Give us a brief overview. We'll go into more detail of your other paper, but brief overview of what you were trying to do in that paper.
So very briefly, Sean, I think the main point of this paper is that neural network can really extract information at the level of the field, but can also marginalize over.
Just a second. I've gone blurry. I'll let you keep talking. But Deanna, do you know what might be causing my share screening to go blurry? Maybe just type some comments about if there's an easy thing I can do to fix it. But then, Paco, please carry on. Sorry about that.
Yeah, it's just that. Yeah, basically we showed that a neural network can marginalize over baryonic effects at the field level. And we show this, using 13 different fields that are affected by baryonic effects in many different ways. These are coming from state-of-the-art hydrodynamical simulations. And
Okay, so let's go a bit more slowly and unpack some of these words. So fields here you're talking about, there might be the field be the density of dark matter. It might be, I guess, the temperature of gas.
yeah, for instance, something, you don't have to really use summary statistics. You can just take, for instance, I don't know, the image of the
Okay, so
galaxies that you
summary
observe.
statistics again, I think we'll have to
Sorry.
go even more slowly. So I guess summary statistics, you're meaning an example of a non-summary statistics is literally kind of all of the information inside the simulation, and then a summary statistic is like some simplification of that, like just number of blobs of dark matter, which is, I guess the technical term is a halo. I guess we'll get into that because the main talk is about subhalos. I've gone blurry again. Oh well. But
Yeah,
just leave it as just you talking.
yeah, it's just that then basically you can pretty much like really extract all the information that is in whatever thing you observe, even if you have some processes, physical processes that are not very well understood theoretically. So the best thing that you want to do is to marginalize over these things.
Okay,
And
and marginalizing, I guess, means sort of averaging over them so that you're not you sort of take the average of the whole distribution of that thing.
yeah, basically you say that whatever thing this particular effect could be causing, you basically kind of consider all the possible things and say that, whatever thing happened, I'm already taking this into account, more or less.
Okay. All right, cool. So that's been 10 minutes. So let's move on. And I see paper 8 of this most popular things is actually the paper we're planning to talk about today. So we can get to that. Yep, cool. So in the meantime, do you want to there were a couple of questions I was going to ask to help introduce you. So let me just find what they were again. So yeah, very briefly, what's your background in terms of not institutional background, but kind of where do you come from? What language do you speak? What's your cultural heritage?
So I'm a Spanish researcher. So basically, yeah, I have, I will say, live most of the time of my life in Spain. Then I have been in Italy. Doing my PhD, I have been in many different countries like Germany, Canada, the US. Then I went to the US in New York, where I have been for quite a bit of time now. And yeah, I speak Spanish, a little bit of Italian, and maybe I don't know what you will consider my English to be. I never say that I really speak English.
It
Something that
seems completely fine to me. I mean, I don't know if we've ever sat down and discussed deep philosophy in English, but anything I've ever discussed with you has been totally fine. Yeah. Deanna has done a few non-English streams in particular, or maybe only Spanish ones, but Deanna speaks more than just Spanish. But I think you've only done Spanish ones. So yeah, you should join her for a Spanish stream at some point. Get in touch afterwards. Maybe I'll answer that question as well, because I've never actually properly introduced myself in that sense. So Sean, I grew up in New Zealand, here in Auckland, where I'm currently living, and spent 10 years in Europe getting my PhD and doing a few postdocs, doing a few sort of post-PhD jobs before coming back here. And yeah, culturally very much a kind of English language, but small outpost country. So New Zealand has a kind of well, I guess we're seeing this in the COVID thing, very isolated sort of perspective on some stuff, but very Anglo-centric perspective on a lot of other stuff. So another question decided I was going to ask all guests is, what is an interesting story related to your physics or like experience of being a physicist so far?
yeah. So as I say, I have been traveling. I have been living in several countries. I lived 4 years in Italy, and then I have been basically living 5 years in the US. And something that I find quite remarkable is that I don't think the US is very, let's say, different to Spain in terms of culture, maybe even the language itself is kind of close. But one thing that I found it was very surprising to me is that after being in the US for quite a bit of time, I still think that, many of us from Europe, even if, someone coming from Finland who speak a completely different language, and I will say has a very different culture, probably even more than, most of the Americans, being Europe so diverse, still I think there is many more things that are very similar to us, and is kind of very different from, I don't know, like let's say the US culture, which is I found that really remarkable. And sometimes, yeah, you don't realize sometimes these things when you really go out of Europe, but it's quite amazing. Yeah.
Cool. I was just checking. I don't know if the YouTube thing has actually started, but I probably won't try and troubleshoot that today. I'll just do a better job in the future. Yeah, my own story is kind of quite similar in terms of not being about physics itself, but about cultural stuff. And Deanna might find this interesting because she's just moved to Helsinki. But I, as a New Zealander, spent 3 years in Finland and sort of in total about 6 years in England as a student or postdoctoral researcher, and found a much bigger cultural shock, or not bigger, but on a more kind of profound level in the UK than in Finland, which is perhaps surprising given that on a superficial level, New Zealand is a lot more similar to England in terms of language speaking, and probably the largest number of people in New Zealand would trace their cultural heritage to England. I guess that there's a large Maori minority and certainly immigrants from all sorts of other places that aren't England, but probably the largest single ethnic group in New Zealand would descend from England. But yeah, England being this very densely populated and very old country had a very different culture to Finland and New Zealand, who are both smaller population density and relatively new countries. Obviously, people have lived in Finland a lot longer than they've lived in New Zealand. Even the Maori have only lived there for, say, 1,000 years, whereas Europe's been inhabited for, I don't know, ever since we became a species. But Finland itself as a nation is very fresh. And so I found I guess the anecdote I like to tell maybe is whenever some world event would happen, the headline news in the UK was always, what is the UK going to do about this? Whereas the headline news in New Zealand and Finland is just, okay, a civil war's broken out in Syria. Whereas in the UK, immediately the Prime Minister is being asked, when will we intervene? It's a bit shocking to little New Zealander that would even be a relevant question when it's happening in a completely different part of the world. Okay, and the last question to introduce yourself: what physics problems keep you up at night? So the reason I want to ask this question is I want out of this kind of whole project of Trenches of Cosmology to give the people watching an idea of like what it actually is that cosmologists are thinking about, not just what is like exciting. Black holes are exciting and the early universe is exciting and this and that, but what is it that we as cosmologists are trying to solve? And so I thought that, the thing that, like, when you find yourself trying to go to bed, but there's some problem you're wondering about, what is that problem?
Yeah, so this is shown something that I've been thinking a lot for many years, and I will be working on this for many years to come. Is that basically, when we do these cosmological surveys, we are only able to really read a piece of the information that is in the universe. The universe, we believe, that can be described with some parameters, some fundamental quantities, and we are only able to read a small piece of all the information there. And what I really want to do is to really read all the information that is in the universe. I know that this might sound like a bit crazy, but that's what also many other people I think are doing. So
Cool. For me, I sort of three things immediately came to mind when I decided I was going to ask you guys this question. One of them is, it's not something I'm working on at the moment, but I worked on quite a lot for sort of 3 or 4 or 5 years, 3 or 4 years ago, is how to measure observationally the underdense regions of the universe. How you, because these are some of the more interesting parts of the universe for a couple of reasons. They're interesting because modified gravity models would be more relevant in these areas because we've probed gravity in denser regions like the solar system, and even the expansion of the universe is probing gravity. But in very underdense regions that are so lacking in matter, some modified gravities models would start showing extra forces there, and they have a kind of way of hiding the new physics in dense regions. It's called screening, but in essentially by increasing the density, the extra force gets suppressed. But then in an underdense region, this extra force would be relevant. But by their very nature, underdense regions are very hard to see. And so far, people do this with a concept called a void. And I worked on voids for maybe even a quarter or a third of my papers are on voids, but I don't think it's the right way to be doing it, because I think voids don't exist. The whole thing is just you have an algorithm that finds a void, and then it's finding what the algorithm finds. It's not finding some isolated thing in the universe. But I don't think I want to go into lots of detail about that. But yeah, how to observe in a consistent way the underdense regions of the universe. And then I would also say probably the quantum measurement problem. What is happening in quantum mechanics when you make a measurement? Even though it's not my field of research, I find myself worrying about it when I go to sleep regularly. Cool. All right. We can ask Helen that same set of questions when she comes on. We might have some small technical difficulties in 20 minutes when she comes on, because she's never joined on HAPS before, and we'll have to get her in. But we can deal with that when it happens. So yeah, let's get started. What we'll be talking about today is a paper that Helen and Francesco wrote together with a bunch of other people using machine learning. So we'll get to a second what machine learning means, to better predict the properties of subhalos, which we'll also get to in a second. But I wrote myself a sentence which is essentially like a English language summary of this, which is that it's AI, or artificial intelligence, predicting the masses of stuff in a simulation without knowing the mass, and doing better than any previously known laws or patterns that we're aware of do. Do you think that's a pretty good summary of, in a non-technical way, of what you guys did, Parker?
I think so, Sean. Yeah.
Cool. All right. So then the more technical sentence would be: a trained neural network predicted subhalo masses to very high accuracy using just 11 parameters, 3 of which were most important. So if you agree that that's a good technical summary, we can then start unpacking what each of these terms mean. Is that a good technical summary? All right. So let's start with neural network. What is a neural network? And I have a picture that I decided I would show at this point, which should come on the screen soon, and we'll change the style so it's big. Cool. And because this is sharing this shouldn't go blurry because it's an image rather than me sharing my screen. Do you want to have a go at unpacking what a neural network is, or do you want me to go and then you can just tell me where I went wrong?
Yeah. So let me see. I think the way that I will describe this is some kind of, let's say, mathematical structure where basically you have some input, you have some output, and you are basically trying to find the relation between these two. So the relation might be given by a function that is, it could be a very complicated function that we don't maybe know how to write down. It could be really complicated. And this neural network is basically something that is going to approximate this function. And this function can be something completely general. So mathematically, the way that this works is that you have some input variables, and then you have these neurons. So usually each neuron will receive the information from your variables. So let's say if we are talking about humans, every person might have some, let's say, labels like your age, your sex, how tall you are, different things. So, and one of these neurons, that is what Sean is showing in this diagram with the different, I think, like circles, is just going to take as input all these variables, and it's going to create like a linear combination with some coefficients. Like in principle, some coefficients. And the idea is
and linear in this sense would mean that, looking at this picture I've got, if you doubled the spin, its input to the final answer would be doubled, and if you doubled the stellar mass, its input would be doubled in some way. And non-linear would mean that if you double the spin, who knows what its input could do? It could even decrease the input to the final value. That it's not this kind of proportional sense.
Exactly. And then basically every neuron will create some linear combination of these, and then will you basically have what we call nonlinear activation function. That is that you perform some nonlinear operation on this already linear combination, and then basically you move on. So this neuron will produce a new number, and every of the neurons that Sean is showing in this diagram will be a new number, and then you can pass these numbers into a new layer where you have different neurons, and at the end of the day you will end up with the property or the output that you want to predict. And basically it's a way to write a relation between the input and the output, where you in principle have thousands, even millions, or even billions of free parameters. And the idea is to tune the value of these parameters to really find this relation between the input and the output.
One of the things I find kind of fascinating about this is that people borrowed ideas from neuroscience, right, to develop the theory of neural networks. Like you used the word activation function or activation
Function, yeah, exactly.
Activation function, and I think what that means, correct me if I'm wrong, is that, for example, for the velocity neuron, that there's like some minimal value of the velocity or parameter that activates the neuron so that it will send something onto the next level, and if it isn't activated, it will just send a very, very small amount to the next level. And apparently that's how our neurons actually work, that they have to receive a certain voltage, and once they get to that voltage they fire and then send an electrical signal down the axon to the next neuron, or down whatever comes out of the neuron to the next neuron. And that, for whatever reason, perhaps not fully understood, I mean perhaps understood better than my speech is going to give an idea of now, because I'm not a neuroscientist, but it's not fully understood why that works so well. But then, yeah, we borrowed that, in we being humanity, not cosmologists, but borrowed that to make these neural networks, and cosmologists then borrowed neural networks to do things like what Paco is doing. Yeah, to be able to say in a way that isn't achieved just by like doing a goodness of fit with a pre-assigned function, that like, oh, I'm guessing that the black hole mass is going to contribute in this way, and I'm guessing that the radius is going to contribute in that way. Now I've got my example formula that I'm going to just fit to. Oh, it's not a very good fit. Okay, let's try again. Let's find another formula. But this kind of, by being nonlinear and allowing neurons to turn on and off, it finds a way to fit. You were sort of saying a function, but we from the outside don't know what function it's kind of found, but it finds a way to be predictive, in the sense that if you then give it the gas metallicity, the velocity dispersion, the star metallicity, blah, 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 blah. Don't worry if you don't understand what these words mean. We will get to it in a second. This is just to talk about neural network at this point, but give it various inputs. It will, yeah, combine them all to give a prediction for the final value, even without you having to give it that function. Yeah, cool. One thing I wanted to mention here is, so yeah, like it's a little bit of a black box. I think that's kind of researcher jargon for what would normally be relevant on a kind of experimental thing, where someone gives you a black box and you plug a cable in one side and a signal comes out the other side, and maybe this black box is super useful because maybe it produces a signal that is exactly the kind of signal that you need to do some thing. I mean, to be honest, desktop computers nowadays and laptops are kind of black boxes. We don't know what they're doing on the inside. We put the power in and it just magically, does all sorts of complicated things like live streaming to the rest of the internet. But the idea here is that, yeah, like your algorithm is a bit of a black box. You don't know what's going on inside of it. And I think some researchers are a little anxious about the black boxy nature of machine learning, and I don't know, I've even heard some people say that it's impossible to do real science with it because you don't know when it's going to go wrong and things like that. And I came up with a kind of what I thought was interesting metaphor for this, which is that when you have like a professor and their graduate student doing research for them, to their professor, their graduate student is to some extent a black box, because they're not sitting down and holding the student's hand and working through every single step of the way. They're just saying, oh, well, what if you change the gas metallicity a little bit? What happens to the final value? And the graduate student understands what they're doing and goes away and calculates the output, but the professor doesn't know all of the nitty-gritty details. So in some ways, machine learning, once you're at the professor level, is not so different. Maybe at the graduate student, when they actually understand everything level, it is a little bit different. But yeah. Cool. So if there are no questions, I mean, please feel free to ask questions if we're accidentally skipping over details and you're not fully understanding a word we used. But if not, we will move on from neural network. So as we go
And
on,
also,
just think of a neural network as this thing that takes in inputs, a set of numbers, activates neurons in a way that is not chosen by the researcher in advance. It's process of whether to activate a neuron or not is based on training it. So you know the answer and you give it a bunch of inputs, and it just iterates and iterates and iterates, changing when neurons go on and off until it can get the answer you've told it is the right answer really, really well. And then you take this and you apply it where you don't know the answer, and you hope it does a good job of giving the same answer, of the correct answer. So the difference though is if the result is interesting, the professor can't ask the student what they did. Right. Yes. So I think hopefully by the end of the stream we'll get into the neural network version of this. I'll share that on the screen. That's a good point, David. Is it presenting on screen? No, I can't click. Oh yeah, there we go. So yeah, so David's point is that if the student gets an interesting result, the professor can ask them what they did and eventually start to understand what they did. But in the neural network, you can't ask it to explain in language what it did. What you can do though is you can, and this is exactly what Paco and Helen did, and why I found this quite interesting, this specific paper, and probably even why we're now talking about it, is that you can play with the neural network and use its insight in the sense of like what parameters are going into the final value. For example, if you remove the star's metallicity, does it suddenly not predict very well? If you remove the radius, does it suddenly not predict very well? And I'm getting ahead of myself a little here, but they came up with this, they used this thing called a saliency function, which essentially tells you how important different parameters are. And based on that, we're then sort of thinking what physics might be relevant if it's just these three parameters. So yeah, it's not quite the same as an English language, like, or not English language, but human language, because of course you don't have to be an English speaker, but a professor asking their graduate student to unpack it. Maybe language processing of neural networks will be good enough in the future that you can literally just ask your neural network, what have you done? And it'll tell you, but we're not there yet. Or at least if the English language skills of neural networks are that good, they're not simultaneously also, I guess, what am I trying to say? Paco's neural network and Helen's neural network is not one of the ones that has a very good English language skill or language skill. You'd have to somehow unite them. But yeah, we'll get to that, David. That's a really good a good point. So the next thing I wanted to cover is subhalos, because in the technical thing it was a trained neural network predicted subhalo masses. So yeah, let's share this one now. Let's unshare that and share this. Hopefully you now see a very pretty picture. Cool. So let's unpack what a subhalo is. So in order to talk about subhalos, it's probably useful to talk about halos. A halo is a halo in the English language is just talking about like angels that have these, in paintings, these sort of halos around their heads. And so it was borrowed by astrophysicists and cosmologists to sort of talk about what dark matter is doing in the universe. So we're familiar with the concept of a galaxy, like say the Milky Way galaxy is this kind of disk, or if you've got an ellipsoidal galaxy, it's an ellipsoid. These things are quite small. Now, obviously the Milky Way is enormous by human standards, by the solar system standards. But if you think about the mass that is in the Milky Way, that in the early universe, when everything was much more homogeneous and then collapsed to form the Milky Way, the amount of volume that collapsed and is now the Milky Way was much larger. And the reason why the Milky Way has been able to get very, very small is because it interacts with itself, and it can give off energy and just get smaller and smaller and smaller. If you think about something that like Earth orbiting the sun, it has a certain amount of energy which is keeping it at its radius. If it was to lose some of its energy, it would fall gradually into the sun. Or if you were to give it more energy, if you gave it more velocity, more speed, its orbit would then be slightly further away from the sun. So in these kind of proto-galaxies that have collapsed gravitationally, the baryons, the ordinary matter, are able to interact with each other and gradually lose energy and then eventually form these nice disks. But dark matter, at least most of dark matter, doesn't interact. So whatever volume that initially collapsed, it keeps close to that volume, maybe 2 or 10 times smaller, but not 1,000 times smaller. So now you might be starting to understand why it's called a halo. That you've got a galaxy like the Milky Way, this thin disk that has a certain size, and around it you have this halo of dark matter, this big blob, bigger in volume but also bigger in mass of matter. So this here in this picture is a simulation snapshot of a cluster of galaxies. I think the orange stuff is supposed to be hot gas. It might not be the best thing for showing a halo. What it does show is subhalos, where you've got kind of the central region that has most of the hot gas and hot matter, but then orbiting any halo are other smaller sub accumulations of dark matter that collapsed on a smaller distance scale. So this blob of dark matter is made up of lots and lots of smaller blobs that are all kind of co-orbiting the bigger mass. And then in principle, a subhalo is made out of its own sub-subhalos that are orbiting that little subhalo. So I've talked for a long time now. Paco, is there anything you feel like I didn't emphasize enough or got wrong, or anything else you want to talk about when it comes to subhalos?
Maybe in a slightly complementary way, Sean, is maybe for every galaxy, we believe in the universe, like the large majority of them will have some halo of dark matter, some diffuse concentration of dark matter around it, and that's basically a subhalo.
Yeah. Cool. I wanted to add one little thing about why one might care about subhalos. So we've just talked about what a subhalo is. It's well, I mean, a subhalo is then, I mean, every subhalo is a halo, and I guess, yeah, a subhalo is just a halo that's inside a bigger halo. But I don't think necessarily for this paper it actually matters a lot whether the halo being considered in this analysis is like the granddaddy of all halos that isn't inside a bigger halo. It just matters that it's a gravitationally bound blob of dark matter, I guess, is the crucial thing. Why should one care about these things? I think for me, the reason I find subhalos very interesting, and again, why then this paper caught my eye and why I wanted to talk about it, is once you get to the smaller and smaller subhalos and sub-subhalos, you're getting to quite small distance scales. Again, I mean, you'd have to be a cosmologist to talk about the Large Magellanic Cloud as a small distance scale, but I am a cosmologist, so I'm allowed to say that the Large Magellanic Cloud is a small distance scale. When you're considering the properties of the universe as a whole, that sort of distance scale does become small. But they're small in that sense, that they're not the distance scales that things like the cosmic microwave background are easily probing, because we just don't have telescopes that are measuring on the small enough angular scales to probe these. And even if we did, the anisotropies in the cosmic microwave background are very, very small on the relevant distance scales. So you'd need to have very good theory and a very, very powerful telescope to probe these scales. Whereas a subhalo, it's there, and you can, for example, the Large Magellanic Cloud is something that we can detect very well. We can detect that with the oldest telescope in the world, our eyes. You can actually see the Magellanic Clouds. So what these things tell us is a little bit about how gravity works on these smaller distance scales, and how the initial fluctuations in the density of the universe were like on those distance scales. And I had planned, but I ran out of time before preparing this to prepare to show you some images of simulations that run with cold dark matter and another thing called warm dark matter. So warm dark matter is this idea that dark matter might have a little bit of kinetic energy, not a lot. If it had a lot, it would be called hot dark matter, but a little bit. And I think if for those who've sort of caught a lot of my streams, we've talked about neutrino masses in the past. So neutrinos are a component of dark matter that would be warm dark matter. They're moving quite fast. And what that means is that the smaller objects aren't able to capture them. They just have enough kinetic energy to travel through the smaller objects and not be bound by them. But the bigger objects, the very, very large halos, do have enough gravitational pull to capture these neutrinos and other types of warm dark matter. So subhalos are therefore a really good way of telling whether the dark matter is warm dark matter or whether some large fraction of the dark matter is warm dark matter. And if I was to be showing you an equivalent image to this one that's on the screen at the moment, but run with a warm dark matter simulation, what you would see is you'd still have this very big, bright central halo, but the orbiting stuff around it, instead of being occupying like tiny little threads, these blue threads and separate isolated halos, what you'd get is just a way more diffuse blob. In other words, you wouldn't have as many subhalos. So subhalos are interesting in that sense, that if you can find them and measure their masses, you're determining whether dark matter is even clustering on these smaller scales or not. In that sense, the Magellanic Cloud is still quite large. The mass of the Magellanic Cloud is, I think, maybe 2 or 3 orders of magnitude larger than the smallest subhalos we've been able to measure gravitationally, which I think we measure via their effect on light lensed by their parent halos. That there's like little kinks in the lensing. So that's one reason why I find it quite interesting. Is there another reason you'd like to talk about, Paco, about why subhalos are interesting? I mean, other than the fact that everything is interesting, measure everything, but
I always see subhalos, like the apartment where a person will live, right? You are a person, you are the galaxy, and you live in an apartment, so the apartment is the subhalo. So you will be affected, I mean, if you live in a crappy apartment, I don't know, maybe this will affect how you are. So yeah, it's kind of interesting to look at subhalos.
Okay. Yeah. I guess, they'd be the environment in which, I guess most of the mass is in a subhalo of a halo. And in some sense, the Milky Way is a subhalo of our local galaxy group, which encompasses us in Andromeda and the Magellanic Clouds. The Magellanic Clouds are subhalos of the Milky Way, and the Milky Way and Andromeda are subhalos of our galaxy group. And our galaxy group is probably some subhalo of some future thing. I don't know if we've yet collapsed into the big thing that it would be. The Virgo supercluster. Am I getting that right? Are we part of that, or is that not? Are we not gravitationally bound to that? I can't remember.
I'm not remember, Sean.
Okay,
Yeah.
never mind. If Deanna's still awake, she can have a guess. Okay, so that's subhalos and why they're interesting, and that's neural networks and how they work, at least at a kind of broad, non-technical level. So now we can get into the details about what Paco and Helen actually did. So maybe now I'll let you do the first introduction of this concept using this image that's coming on the screen now. No. Okay, I want to remove this one. Maybe this will work. Cool. So what are camels, and what are you guys doing, and how does this relate to machine learning and neural networks?
Yeah. So the idea of these camels. So camels start for cosmology and astrophysics with machine learning simulations. So the main idea here is to run a bunch of cosmological hydrodynamical simulations. So these are state-of-the-art simulations in the sense that this is the most sophisticated simulation, for instance, that we have in order to model things like galaxies that are something incredibly complex. And the idea is that there are so many different pieces going on in this particular thing that is a very, very hard problem. So sometimes you need to touch this ingredient, should I do my black hole larger or smaller? Or should I make, the energy that my supernova release larger or smaller? So there is, it's very complicated to look at all these possible variables. So the idea of camels is to basically run simulations where you have many possible different universes. There might be universes where you have incredibly large black holes in galaxies. And then some of these black holes will release so much energy that they will completely destroy your galaxy. So at the end of the day, you end up with no galaxies. Or maybe you have some universes where the fraction of the energy contained in the universe in matter is very large, and this will also give rise to maybe very heavy galaxies. So the idea is that once you are able to simulate many possible different universes, probably a neural network will be able to kind of interpolate between all these different possibilities. And this is going to be very useful for us, because now we cannot be running simulation forever and ever. These simulations are very expensive. Basically, for those of you that might not be so familiar, if you will be running the simulation that we have run here in your laptop, I think you will have to wait something like, let me see, I don't want to say something wrong, but I think something of the order of 1,000 years or something like that. So, of course, we use supercomputers for doing this, but these are incredibly expensive simulations. And the idea is that once you have all the simulation run, maybe a neural network will be able to, if now you need to explore these different configurations, maybe the black hole parameter is in this range, maybe you don't need to run a simulation anymore. Maybe a neural network will run the simulation for you. And that's basically, I think, Sean, the main idea for this.
Cool. And the simulations, I guess let's unpack what a cosmological simulation does. So I guess there's the vanilla simulation, which would take only gravity, and it would say, and let's be fair that 80% of the matter in the universe is dark matter, and most of dark matter only interacts through gravity. So these vanilla gravity only simulations are not ridiculous. And on the larger distance scales, they're actually quite accurate, because in order to interact non-gravitationally, you do have to be close to each other, right? The stuff that does interact with itself, the baryons, the stars, and things like that, are electrically neutral mostly. So they're not having these large range forces like gravity does. Like the sun interacts with us gravitationally, but I guess it also interacts with us. It sends light to us, but maybe that was a bad example. But the center of the Milky Way interacts with us gravitationally, and it's not really influencing us in any way non-gravitationally. And we're made out of stuff that does interact non-gravitationally, but in order to model how the Milky Way affects us, we just use gravity. So the vanilla simulations just use gravity. They set up the initial conditions based on some model of what the initial conditions of the universe should look like, and I guess that's one of the parameters that can be varied over what the initial fluctuations in the universe's density can be like. And then literally, I guess most of the simulations, or some large subset of them, just coarse grain on some scale and have like particles of matter that are very massive particles that are moving around in the simulation. They may be 1,000,000 times the mass of a sun, of a star, but then they kind of orbit around and are influenced by gravity. And they'll tell you what the universe is like on distance scales that are large enough that when you coarse grain 1,000,000 times the mass of the sun is not, knowing things on a smaller distance scale than that is not relevant. But then if you want to go to small enough distance scales or be accurate enough, gravity alone isn't enough. And that's where this word hydrodynamical solver becomes important. And so this is not something I'm a big expert on. So Paco, you might need to jump in if I start going a bit off the beaten track or off accurate. But the word hydrodynamical, I guess, comes from water. That there must have been some sort of like solver that treated. So okay, what am I trying to say? It adds in the concepts of pressure and things like this, that the non-dark matter parts of the universe give off light, they affect each other, and they have a pressure that if you start to collapse too much, they'll actually resist it, they'll push back, and they'll also give off energy and collapse even further. So it's no longer quite so simple as just using gravity. Do you want to sort of talk about maybe how, in the simplest iterations, one starts adding in these effects? Because certainly a solver that is including non-gravitational effects is not working at such a small coarse graining scale that they're like actually solving the nuclear physics of a star, right? Like it's not solving down at the solar system level. But how do you add in these effects without going to that sort of level?
Exactly. So, as you were saying, Sean, for this traditional simulation, like the M body that is only gravity, for instance, you can never produce a galaxy with this. There is no way, right? Because in a galaxy, you have stars, you have gas, and in this simulation, you only have dark matter. So, with this simulation, you never produce galaxies. If you want to produce galaxies, then you need to model the evolution of the gas in the universe, and you also need to produce stars, you need to produce black holes, and you need to produce all the things that we see. So that's why you need these hydrodynamical equations. So the main idea is that you have dark matter, and dark matter will only basically feel gravity. But then in this simulation, we also have gas. And for gas, we also know the equations governing the evolution. These are the fluid equations that we know very well. So then we can also model like let's say, like the time evolution of the gas in the universe. And what happened typically is that, for instance, you can have dark matter. That matter can concentrate, and and it will it will produce like a gravitational well, and gas can fall into this gravitational well. So usually when gas fall into this gravitational well, potential well, usually it can cool, can release some energy, and at some point it's gonna be so dense the gas, and it's gonna be cool enough that it's gonna give rise to, for instance, a star. So that thing, Helen, sorry, Sean, I just saw, I think maybe Helen joining.
I guess we're muting and
So,
unmuting each other. I guess Helen has joined. Welcome, Helen.
Oh, hello. Hi. Sorry I'm
hi,
late.
Helen.
Yeah, no worries. We warned everyone you would be late. So let's maybe just you can just say hello, but then we'll let Parker finish his thought, and then you can like properly introduce yourself. So you were just talking about gas cooling in the center of a gravitational well, and I guess it's mostly hydrogen, or is it treated entirely like hydrogen? You're not sort of like distinguishing between hydrogen and helium and other stuff in this sense. It's just one thing.
We keep initially like the let's say the fraction of hydrogen and the fraction of helium that is in, we believe that is in the universe. So in that sense, we model this properly. And at some point, yeah, you will form a star. The scale where a star form is much, much, much smaller than the typical scales that we have in this simulation. So it's completely impossible for us to really resolve all these different scales. So basically, we
Cool.
cannot really resolve how a star form, and that's why we have this thing that we call satellite physics. Basically, we use some recipes, kind of artificial recipes, to model these astrophysical processes.
Hmm.
And then, when you have a star, this star at some point might explode with as a supernovae, and this star can also produce, many different metals like carbon, oxygen, all the different things. And this will also enrich the gas that it was, in the intergalactic medium.
Mm.
And this is the way that
Cool.
we evolve this.
Yeah, awesome. Okay, so let's put a pin in that particular point and let Helen properly introduce herself.
Oh
So
yeah. Hi.
I guess what were the questions I wanted to hold on, just have to reopen them. But yeah, what is your kind of background, not necessarily in terms of institutions, but where your cultural background and what is it that interests you about physics and things like that? If you
Oh
want to.
yeah. So I'm from Shanghai, a city in China, but I've grown up in the U.S. So I speak very little Chinese, and yeah, I guess I've always had a general interest in astrophysics and cosmology because of the beautiful like mysteries that rise in this field and the questions that cosmologists are trying to answer, tackle the most fundamental laws of our universe. And it's very exciting to think that we may be able to solve and understand the like the physical processes of structures that were formed billions of years ago in the early universe. So for me, these are like the biggest questions that humanity can ask, and the scope of them are so large compared to our own lives, which makes them more fascinating. I recently started research. Actually started in high school, and I feel like over time I grew to absolutely love the hands-on experience of solving problems and working with data to unveil something beautiful. And for me, there's always an element of surprise because even though you have some idea of what to expect, you do not really fully know what the outcome will be until you perform like the experiment, and slowly the pieces start to come together and you learn so much new things from the unexpected.
Cool. And I guess the second question is like, do you have an interesting story related to your physics experience so far? I did only come up with these questions a few hours before the stream, so Helen and
Interesting
Paco might not have
story.
had that much time. So if you haven't had time to think it through, Helen, no worries.
Like an interesting story of how I got into physics.
Oh, just about anything in your kind of physics experience. I mean, one interesting story I might tell about you is that you're currently still an undergraduate, and yet we're the lead author on this paper that we're discussing. So that's kind of interesting in its own sense. So if you don't have an alternative interesting story, you could talk through how a second year undergraduate becomes the lead author of a paper that is interesting enough that cosmologists are talking about it in their journal clubs.
Yeah, thank you. Yeah, so for this paper, I've been working with Paco for several years now, since I think my third year in high school. And he introduced me to the idea of machine learning, which back then I had no idea about. So it was really cool to start from the bottom and learn about machine learning and also learn how to apply it to cosmology. And it took me a while actually to get some good results because the first two projects that we worked on, I was still, I guess, rusty with the machine learning techniques, and I wasn't able to produce any good results. But just surprisingly, with this project, after a few tries, we started to see like things that started to make sense, and the more exercises we tested, the better the results got. So yeah, it was kind of a surprise.
Cool. And I guess the last question was what physics problems keep you up at night? What is it that makes you unable to get to sleep? You're just like, I want to know the answer to this annoying
Um,
question.
hmm.
No worries if I'm putting you on the spot. As I said to everyone watching a few times, I only asked you guys these questions like 2 hours before the stream started, so don't worry about it.
Yeah, well, I guess right now the physics problems that keep me up at night are the problems on my homework sets because
Fair enough. Fair
they
enough.
take a while to think through. Um,
Totally fair enough.
yeah.
Awesome. All right. So we were probably just finishing a discussion on the simulations that are going into chemicals. I guess if anyone wants to look up the actual kind of simulations and read material about them, it's these illustrious simulations. Maybe I'll type the word into the chat. Is that right? Is there anything else either of you want to say about these, like where someone should go if they want to learn about it?
Yeah, it should be either Illustris TNG, it's called, but there is also another set called Simba. So yeah, there are similarities and also some things very, very different. But yeah.
And TNG is like, that's like the next generation, isn't it? Right. So there was the
Yeah.
illustrious, and then they made improvements and needed to know what to call their improvements.
Yes.
And what do you know off the top of your head what Simba? Am I right to capitalize it because it's an acronym?
I think so. I'm not sure the history. I think the main person behind this is Romilda. I think he was a professor in South Africa for several years, and probably is related with his South African connection, but I don't know all the details.
Okay, so I think we have hopefully now we've talked about neural networks and how they sort of take inputs, have these non-linear activation functions that turn neurons on and off, and as a result of that, come up with a kind of black box, but a way of predicting certain properties. We've talked about subhalos, which are these blobs of matter that kind of have this almost web-like hierarchical structure where you've got a small, whoops, hand on the screen, a small blob that's inside a bigger blob that's inside a bigger blob, and a bigger blob might have many smaller blobs sort of orbiting it. And we sort of saw that in this image here, which I'll just put up briefly, that you see the central blob and then lots of like sub blobs around it. And now hopefully I can get rid of it. No, that's not going to get rid of it. That'll get rid of it. Cool. And the teaser is that we want to measure the masses of these subhalos within simulations. So the simulations we've now sort of talked about, they are mostly gravity, but then you also have this gas component which has a pressure and can lose energy, can emit energy and thus get more bound. And then once it gets small enough, there's this recipe for producing supernovae and things like that that will further affect the evolution. So now we want to put all of this together. We want to find a neural network that, using a certain set of parameters that are available to you from the simulation, predict the mass of a subhalo. So I was going to share my screen, but we had problems with that. But thankfully, this neural network image has all of the relevant things. So I'm going to make it big. Is that going to work if I make it the primary spot? Or is it going to be squashed? I think it might be squashed. No, that didn't help. Okay, we'll do it like this. One of us is not going to be on the screen. Oh, no, we're all on the screen. But it's still small. Okay. Let's see the logistics of doing this. How do we want to do it?
You can take me out, Sean.
Take you out briefly. Okay.
Yes.
Well, and then whoever's talking, I'll put back in as they're talking. So what we do now is we want to say, okay, we want to measure the subhalo mass. And we have available to us, well, more than these 11 plus 1, the plus 1 being subhalo mass properties. But I guess these are the ones that the two of you and your co-authors decided were the relevant ones to use to train your neural network. So you're putting in, you found a subhalo within your simulation, and you're measuring all 12 properties, including its mass. Because when you run a simulation, you're God. You know the mass of the subhalo. You don't need to predict it. But the idea is to look for patterns amongst these 12 parameters that might be useful to learn more physics. And then I guess ultimately the goal is to have here purely observational properties that we can measure with a telescope and then predict the subhalo mass where we're not God, where we can't just count the mass inside the subhalo because we can't go out to the subhalo and actually do that. So let's talk through what these properties are relatively briefly, but I think this is where the most interesting, perhaps, physics is going to come in, is that why we think as cosmologists that these 11 properties are interesting things. First of all, in their own right, interesting, and then second of all, why they might be the things that are helping us to predict subhalo masses. So let's just start from the top and work our way down, unless the two of you have a preferred other order. Speak up if you do, otherwise we can just start at the top and work our way down. Nope. Okay, so yeah, let's start with spin. What is the spin parameter here?
Yeah, so we define the spin as just like the modulus of the 3D spin vector. So
so this is the angular momentum, I guess, of the subhalo itself. How much and then modulus, you mean the magnitude of the angular momentum rather than the direction. I guess one wouldn't expect the direction of angular momentum to be correlated with the mass of the subhalo at all. And I guess that's because we assume the universe is isotropic, that it looks the same in every direction. So it shouldn't have a preference. So Paul commented that what keeps him up at night is the number of people out there in power that are making decisions based on the opposite of artificial intelligence. Yeah, I guess you wouldn't want to go too far in the other direction either, Paul, where you had some artificial intelligence, at least not with the current capabilities of artificial intelligence that are making all of our decisions for us, because then it might do something that we weren't expecting. In some ways, we do have that already, I guess. This is completely off topic in terms of cosmology, but Facebook and YouTube and other things have their algorithms, right, which are artificial intelligence. So what we are shown on Facebook and what we watch on YouTube, and probably even more orthodox news sources like newspapers online, they have to pick what they put on the front page. They're making decisions based on artificial intelligence. And I guess we don't, because they're black boxes, we don't fully know what is going into it. And I don't know, that leaves me a little bit anxious that because maybe the algorithm decides that the best thing to show is something that gets people worked up and angry, might not be the best for keeping democracies healthy. But I also agree that people making decisions are probably not being careful enough. Anyway, good comment and cool. So now, go on, Paco.
If I mention, so this is actually, someone told me this a few years ago. I don't know if this is actually true or not, but this is also something that we should be aware. So for instance, it seems that what they told me is that here in the US, sometimes when you go to court because something happened, there used to be one of these, like, for some reason, the judge can also use some machine learning method to see if you are guilty or if you are going to be, whether something like that. And basically, what it was very interesting is that this machine learning or this network was finding a correlation that if you were black, you are very likely to be guilty. And this only happened, of course, because when you were training the neural network, there were many more people who were black, and they were on jail. So it found this completely artificial intelligence that has absolutely nothing to do. So you have to be also incredibly careful when you train your neural network, right? If you have a bias in your data, the network is going to learn this bias. And of course, we have to be super careful with this because this bias is completely artificial. It's not real at all.
Yeah. David had I just shared it on screen, but yeah, the same point. So yeah, I guess we need to be careful with how much artificial intelligence impacts, how much black boxes, I guess, is the crucial part there, are impacting our decision making. Awesome. All right. So, well, not awesome, but let's move on. Yes, Paul, the opposite is real stupidity. So we need to find some healthy middle ground of intelligence when making decisions. So stellar mass, what is, let's maybe do stellar mass and gas mass at the same time, because the interesting thing there, I guess, is the difference between stellar mass and gas mass. Now that there's two of you, I guess we can't I can't just say go and one of you
Helen,
talks.
go ahead.
Oh, okay. Yeah, so the stellar mass is just the total mass of the star particles in the subhalo, and for the gas mass, it's the total mass of the gas particles.
Okay, cool. And I guess the important thing here is these recipes that when the gas gets dense enough, it as I said, maybe before you got here, Helen, but the solvers you're using, these simulations, are not resolving to a small enough distance scale that they're like doing nuclear physics and the gas is actually turning into a star there. And as Paco, I think, said, there is some recipe that, okay, once it gets to a certain density, we're saying, okay, now it's a star and it can do star type stuff. And then I guess here is how many things have reached that point that the simulation is saying that is a star, and how many things haven't reached that point and the simulation is saying that's still just gas. Oh yeah, and then black hole mass. I guess you must have recipes for black holes as well.
Exactly. So this quantity just represents, the mass of the black hole that you have in your subhalo.
Cool. David asked a really good question. I'm going to share it on screen. Essentially, we were talking for a little bit about how in social policy there are biases that the artificial intelligence learns. So is it also true that when we're doing this in a situation where it's less tragic if you're biased, but still important if you want to be a good scientist, that you're as unbiased as possible. I mean, yes, absolutely. Like whatever goes into this simulation, if the simulation these guys are using is wrong, then the machine that's learning based on the simulation is also wrong. I guess maybe that's something you want to go into a little bit. I think this is interesting enough that we can take a bit of a tangent, but you were saying earlier you used Illustris and Simba. I guess this is trying to get at exactly this issue that David just brought up. Do you want to talk about that a little bit?
Yeah, exactly. So this is actually a super good question, and I will say we don't even have an answer. So when we use these simulations, we are making the underlying assumption that this simulation represent more or less reality, but we don't know if I mean, I think we know that this is not true. And to be honest, this is my personal opinion. Maybe in 20 years I will say, oh, why did I say this? But probably simulation will never be perfect. Maybe simulation will never really represent reality. Reality is such a complex thing. I mean, I don't know. We don't know if we are gonna be able to do this. So this is a super good question. There might be biases in our models, but also there might be some physics that we're missing in our models because we have an incomplete understanding of the universe. So using these kind of tools to really work with real data is something that we will have to be very, very careful. And I don't really have an answer of how we are going to do this, but this is a super good question. Yeah.
Yeah, I guess how well it fits. Like, hopefully we get to the point where we can actually show a plot that at least, I mean, you were predicting things from within the simulation, I guess, but you were comparing between simulations, I suppose, that you can see how good a fit your best prediction is. If your best prediction is, and in fact, in your paper, I didn't actually, I haven't prepared any plots. I was going to share screen, but as we know, that gets potentially blurry. But you did have some situations where the best prediction by the neural network was quite bad, and I don't mean bad in that there was a lot of scatter, but just completely wrong. Like you had the line of correct masses, and your network was doing something like that.
Yeah.
So to answer David's question, I guess, when in the example I was just talking about here, Helen and Paco were like comparing different simulations, perhaps different physics in the simulations, and seeing that if they trained on one, then maybe it was biased on the other. Or I think that where it went really wrong was when you changed redshifts and used a certain measure of distance that was, I mean, co-moving distance, but meaning essentially, I won't go into that, but used a certain measure of distance that meant that the result was biased. But in the real world, of course, we make observations in the end. And I guess the crucial thing is your black box actually predicting something that matches reality. And there, unlike in the social situation, if you keep trying and keep making mistakes and eventually get it right, you're not harming anyone in the process. Whereas, of course, if you're using artificial intelligence to make your social policy and you wrongly incriminate 100 people before you get your model accurate, then that's bad. And yes, David, that's true. All models are wrong, but some of them are useful. I mean, I think that's a really important thing to keep in mind, that models are just approximations of the universe. Newtonian physics is in a sense wrong, but it's very useful to describe the solar system. And yeah, these simulations, as Paco said, are wrong. I mean, as I've pointed out, they're not. I just realized I'm not on camera, but as Paco pointed out, then, as I said, they're not, capturing the nuclear physics of stars, so that they are wrong. They're using the recipes that Paco was talking about. But yeah, they're useful to some extent. So is black hole mass anything more complicated than just there is, again, a recipe that when the gas reaches a certain density, you just decide it's not a star, it's a black hole? Is there anything more sophisticated going on that should be talked about?
I'm not a super expert on this, Sean. I think the main idea is the one that you said, but yeah, maybe technically there are some subtleties more, but I think that's the main idea.
Okay. I'll leave myself off the camera now because we're getting back to sort of working through the list, hopefully. But yeah, velocity. Is this then the velocity of the subhalo with respect to its parent halo, or what is it the velocity with respect to? Because of course, as any good physicist knows, velocity is only a relative thing. You're never you don't have any absolute speed.
Yeah, in this case, is we have the simulation, so it's kind of with respect to, I will say, the frame system of the simulation itself, which
I guess that would be the background expansion of the universe then.
exactly is probably with respect to, let's say, the CMB for us, but
Yeah.
yeah, it's really like the peculiar velocity without
Yeah.
once you remove the expansion itself.
Yeah. Okay. So yeah, just to unpack that, the whole universe is kind of expanding, but then as sort of gravitational pull pulls you in a certain direction locally to where you are, you start still expanding relative to stuff that's far enough away from you, but you do have this, as Paco said, peculiar velocity that is in a direction not exactly aligned with the expansion. Cool. Okay, and so then this is one of the parameters. Now, gas and star metallicity. I guess the distinction between gas and star is the same thing as before, but what is metallicity?
So this is one of the things. Helen, go ahead. Sorry.
I don't know. It's okay. You can go.
Please go ahead.
Yeah. So from what I understand, I think metallicity is it's a quantity of the abundance of the elements in the subhalos that are like heavier than hydrogen and helium, but I'm not sure.
Exactly. And in astronomy, as you know, Sean, we are very, I don't know, lazy or yeah. So a metal is anything that is not hydrogen or helium. So metallicity basically is the fraction of mass that you have in any element that is not hydrogen or helium with respect to the total
Yeah.
mass.
Yeah,
That's
or
basically
maybe
it.
lithium, although there's so little lithium that I guess it's not relevant. But anything that wasn't produced primordially in the Big Bang. What I find interesting then is maybe how do you know in this? Is it, I guess the answer is just going to be recipes. But how does the simulation decide when a metal has been formed? Because it's obviously not simulating the nuclear process that produces the metals.
Yeah, so for this, Sean, my understanding is that once you have a star particle and it will explode maybe as a supernovae, then there are all these, recipes from stellar physics. If you have a stellar with this mass, you are going to be producing all these different elements, given the nuclear reactions that is going to take place, blah, blah, blah. And this is the fraction of elements that you are going to release when you explode. And this is basically the way that you form all these different elements.
Okay, cool. And then the simulation sort of follows them gravitationally from then onwards to work out where they end up, or do they just sort of free stream because they've got so much kinetic energy that gravity is not relevant?
The idea is that every gas element itself will be defined with the different fractions of the different
I see.
elements,
Okay,
and the gas itself can, experience
Yeah.
the normal forces.
cool. All right. Now, radius is probably self-explanatory on a kind of abstract level. It's the size of the subhalo, but perhaps when you think about it a little bit more carefully, it's ambiguous. Like, where is the edge of a halo? It's not like a top hat where it's got a certain density and then the density just becomes zero, and it's like, okay, well, that's the subhalo. It's actually got some density that is peaked at the center and is gradually decreasing, but where is the edge? So you have to come up with some definition of radius. What was your definition? Helen?
Well, I'm not sure how they like distinguish between the edge of the subhalo and what's not a subhalo, but for the radius that we're using, one of the important things that we want to know is that from the simulations we're getting the co-moving radius, which is just a scaling of the proper radius, and this distinction actually pops up in our results for the neural networks when we train and test on simulations using the co-moving radius and then the scaled proper radius. And we can see that for these two different definitions, we have very different results. But yeah, I guess that doesn't really answer your question.
Yeah, I think maybe you thought the question was more complicated than it was. I think you choose the definition to be like the radius in which half of the mass is contained or something like that. Is that right?
Oh,
Or
I see. Yes, it's the half mass radius. Yeah, containing half of the total subhalo mass.
yeah. Okay, cool. And then star formation rate is an interesting one. What does that word mean or phrase mean?
So this is shown typically, in your subhalo. Typically, there will be some fraction of the gas in some regions of the gas. There will be actually forming stars there, and basically the rate at which the stars are being formed. This is what this quantity describes. For instance, if you are forming a lot of stars, then it's very different than if you are forming very little stars. So this quantity basically characterizes that property, the star formation rate.
Cool. Two more to go. Velocity dispersion. What is a velocity dispersion? So we talked about velocity earlier, which was the whole subhalo and its motion through the simulation. Now this is obviously something different. What is this?
Yeah, so velocity dispersion here, we measure it for all the particles in the subhalo, and I think it's a quantity of the statistical dispersion of the velocities from the mean velocity of the subhalo. So yeah, it's not technically the actual velocity.
Yeah, cool. So yeah, like a measure of how fast things inside the halo are moving, because although the halo might have some bulk motion inside of it, all of its sub halos and ultimately down to the actual particles of the gas and particles of the dark matter are moving and orbiting and stuff. So this is cool. And yeah, last piece, maximum velocity curve. What is that?
Oh yeah, Vmax. This is just the maximum of the circular velocity curve. So I think it's proportional to, I think, like the square root of mass divided by radius times a gravitational constant.
Yeah, so I guess that's like if I was to say, I'm using gestures, so let me just put myself on screen for a sec. If you've got the center of the halo and you move a certain distance out, and you were to say a particle here has a circular orbit, I guess you're saying that defines the circular velocity, and then your maximum circular velocity is there is some radius where that speed is the maximum, where if you go further in, there's less mass inside of your circle, so you're going to orbit more slowly, and as you go farther out, you're getting further and further out, so your speed will go down, but there's some point where I guess that is maximized. Is that correct? Or
Yeah.
Mm-hmm.
Yep, cool. All right, so those are the 11 properties, and you found 3 of them were crucial. They were the radius, velocity dispersion, and Vmax. So I wanted to have 2 discussions here. One is how you extracted from the neural network that these were the 3 most important ones, because I think that's interesting in a kind of methodological sense. Like, as someone pointed out, David pointed out earlier on, you can interrogate a PhD student and say, why is this happening? But you can't interrogate the black box. But as I promised David at the time, we'll talk about how you did actually interrogate the black box. But second of all, what's going on physically? Why is the radius, the maximum velocity, and the velocity dispersion, why are they more important than the spin, the stellar mass, the gas mass? What is it about these properties that makes them crucial? So let's just start with the how did you interrogate the black box question?
Oh yes. Sorry, were you gonna say something, Falco?
No, go ahead.
Okay, yeah. So to find out like which of these properties are more important for your network, we computed something called a saliency value. So for each of these input properties, we calculated their average saliency values. And this calculation is basically looking at the gradient of the weights in the neural network. And if we have a larger gradient, then it means that that input variable, small changes in that variable will lead to larger changes in the neural network's output. and that would translate into having more contribution towards the neural network's predictions.
Cool. And so yeah, so from that you found that, I guess there was I wanted to share your paper. I'm going to try sharing the paper, and if it goes blurry, I'll just stop. But may as well give it a try. And so yeah, now while I'm doing this, maybe have a chat about why these properties. What physics do you think is relevant that is causing these to be the important ones? I mean, maybe start with the radius, because I think it's probably obvious why the radius is perhaps important to the total mass. But yeah, do you want to have a chat?
Yeah, so I guess we look at radius alone. I mean, the correlation between radius and the total subhalo mass is, if the radius increases, then the mass contained inside a radius would also increase. But with radius and velocity dispersion together, I think as we discussed, the physical meaning behind this lies fundamentally with the Virile Theorem, which uses these two variables. So in our earlier, when we were trying to find the analytic models, these two variables in our earlier attempts showed up a lot, and it was some version, we believe it was some version of the Virile Theorem. But then we found that Vmax, the third important variable, actually plays a very crucial role in the neural network's predictions. And I think we found that this was the case because since massive galaxies tend to have their Vmax at a smaller radius, so like maybe inside a bulge of the galaxy, and this causes the dynamics of the subhalo to be at the small radius to be related to the Vmax. So, which is why we found that Vmax is important for the subhalos of masses larger than 10 to the 10. But in the more massive galaxies, radius and velocity dispersion, these two alone are able to accurately predict the total mass.
Cool. So you mentioned this. I've found this saliency value plot, which is, as you said, the measuring how sensitive, I guess, the prediction is to these properties. That if you change the radius or velocity dispersion by a little bit, how much does it change the weight going into the final prediction? One thing I see a little interesting here is that according to this ranking, gas mass is actually more important than Vmax. Is that something that you think is interesting to talk about, or is that why is that the case?
Okay. Yeah, I think when we were trying to use symbolic regression to find a model for the total subhalo mass, gas mass did show up in several of these equations, but I don't think we were able to provide a physical meaning for why gas mass was playing an important role. I remember discussing with a few others about maybe the role of supernova feedback in which in the simulations, which would maybe cause gas mass to be important, but in the later equations that we found, Vmax started to show up more often.
Okay. Like naively, as an outsider who never played with this data, gas mass seems kind of obviously relevant, because if the total mass of the subhalo is bigger, it's going to have more gas in it, and seeing as gas mass is one of the parameters that you're allowing yourselves to use as an input, it seems like it would be a really good proxy, if not the best one. Like completely naively, that I'd have thought it would be roughly proportional, that if you've got twice as much total mass, you might have twice as much gas mass. Like it doesn't seem like a obvious reason why it wouldn't be proportional. So I was a little bit curious about why it might not be so naively powerful as a parameter.
That's a good point, Sean. I think maybe the thing is that what you say is true, but I think the kind of fundamental thing about this paper is that we claim that this relation is kind of universal. So in this simulation, we have even models where you have, gigantic black holes that can maybe, expel a lot of energy from the center. So you will expect that the gas, most of the gas in a subhalo, I believe, is really living in the galaxy, in the internal galaxy, and maybe in the area next to it. So I believe that this is a quantity that will be very affected by astrophysical effects.
I see.
That's why
That's a good answer. So even if in a typical halo, it might be that gas mass is super important, you want something, as you said, that's universal, that's going to work all the time, or like almost all of the time. And so in these unusual, rare halos, the gas mass is not such a good proxy anymore. And whereas in them, the radius and velocity dispersion has been, it's still, yeah. Okay, that's cool. And yeah, I think we'll start wrapping up pretty soon. I think, Helen, you mentioned this Virile theorem. That is a concept that in a halo that has kind of had time to reach a sort of approximate equilibrium, the kinetic energy and potential energy should be related. I think one of them should be twice the other one, but I've forgotten which one off the top of my head is the double. Is it the potential energy should have twice the kinetic energy, or is it the other way around?
I think the kinetic energy should be equal to twice the potential energy.
Okay. Yeah. So and so there, as you were saying then, that means that, yeah, the radius, velocity, dispersion, and mass should be very intricately related, because the potential energy is clearly defined by the radius and the mass. If you tell me there's a certain mass inside a certain radius, then I can tell you the potential energy. That's just a Newtonian physics that a total mass inside a certain radius will have a gravitational potential at that radius. And then the velocity dispersion is defining the kinetic energy. It's telling you how fast things inside this halo are moving. And so therefore, if I've measured the velocity dispersion and I've measured the radius and I assume the Virile theorem, I know the mass. And you did find that your kind of most naive formula, which didn't fit the data perfectly, but I mean, it did better than a random formula plucked out of a hat, actually was what the Virile theorem would predict. And then I guess as you were saying earlier, the Vmax is able to kind of correct in some way for deviations from the Virile theorem. So just to show, I guess, one of the plots that shows how well your that's not showing how well your I'm not sharing the screen anymore. So you didn't see me showing the wrong plot. Here we go. Let me just make sure it's settled on that plot. Cool, and then I'll share screen again. That should be that. And then this, and then that. Am I getting the hang of this now? Not quite. I think I have to remove me, and then there we go. So this plot on the top left is kind of showing, at least when you stick to the same simulation that you trained the neural net on, but then used it to predict subhalo masses that you didn't train it on within that simulation. This line running up here is the line of predicted mass, which is this axis, and true mass, which is this axis, being equal. So if you're doing a good job, you should lie on that line, because you want your prediction to be equal to the truth. And these dots are then what the neural network is saying the mass should be. Hopefully I've picked the right plot. It's a bit tricky with the oh no, these are the analytic equations. Sorry, this is the neural network here. This is the best prediction by the neural network. Yeah. So it is showing that your neural network is doing a very, very good job of predicting it. And it is interesting that this gets to David's question from earlier, that if, let's say that this Camel's illustrious TNG simulation was the wrong physics, and that this Camel's Simba was the correct physics, this is what the neural network's doing. So yes, it's nowhere near as precise as if it was trained on the correct physics, but at least in this case, the deviations between the physics in the two different models, I mean, maybe Simba and illustrious TNG are both wrong, in which case, oops. But at least if TNG was wrong and Simba was correct, the neural network is still doing a pretty damn good job at predicting these masses. Yeah. So this is the kind of end of what I wanted to show. I mean, there are interesting effects that you spot here, which is that although it can extrapolate to the same mass range, but different like hydrodynamical physics solvers, what it can't do very well is extrapolate to new masses, the neural network. It starts to go completely funky when it was trained up to this mass, you see here. And then when it's asked to predict on a simulation that has better resolution, so it can go to a lower mass, it starts to do poorly. And I guess the same's happening here, that it was trained to this mass, and then it was used to predict outside that mass range. And this is what I think, I guess, drew my eye to the paper, in that their formula, which is now sort of independent of the neural network, they just said, here's a formula, let's try and fit it as much as possible. It extrapolates extremely well to the low masses and high masses. The formula is a very ugly formula. If I show it on the screen, you'll see it's not elegant. It's this one here, but this is a formula that is now a formula. It's not a neural network black box, right? Like, this is what we were talking about, that this is the opposite of a black box. I can see exactly what it's doing. It's ugly, but I know exactly what it's doing, and it's doing a really good job at, like extrapolating to ranges where it wasn't trained. So in some sense, some new, I guess Paco used the word earlier, universal thing relating these parameters, the Vmax, the radius, and the velocity dispersion, is lurking inside of that formula. I guess that the important thing now is to extrapolate more elegantly what the physics is that is being captured by this formula in a way that is more insightful to a human being. But that's what I liked about it, that it's not just giving up at this point and saying, I have this amazing black box that can, basically do what you want to do better than anything else. This is as good as it gets, at least in cosmology. But saying, no, okay, I want to be able to predict outside of the mass range it was trained. And so here's this kind of physics formula that they came up with that is loosely based on Virile Theorem concepts. So cool. That's all I wanted to talk about today. Is there anything that you, Helen, and Paco wish to add before we say goodbye?
No, thank you, Sean. Not from my side.
Cool. Well, thank you everyone for watching, and hopefully I have a good time now, so that I can try and do this every week, and we'll be at the same time every week. So that's 8 p.m. UTC on Sundays, I believe. 9 a.m. New Zealand time is the actual official time, whatever that is. I think it's 8 p.m. on Sunday GMT. Awesome. Well, thank you, Helen. Thank you, Paco, for joining, and see everyone next week.
Yeah, thank you so much for having us.
Thank you, Sean.